All right, we should shut the door because you guys know the 7th grade processes that Pettigrew was lecturing people about. Makes me want to go over there and be like, wait, Mrs. Pettigrew, you mean every day? Not just the days I feel like it? So would there be, just initially gut reaction, any other angles inside of this upper triangle that would be equal to our green angle? No. Where, like, how could I find an equal angle to that green? Like, where could I go? What could I look for? What indicators, sorry, wrong emphasis. What indicators could I put on this image? Because we actually skipped the lesson where this gets, like, initially brought up. What does this at least for sure look like it has true? What looks true? It's not been indicated here yet, but what looks true about this image? Yeah, I'm asking this question poorly. If I talk about this line, the top shape, that actually the lesson we skipped over says he took this parallelogram and copied it. And because the problem that we skipped over tells us that if it's a parallelogram, we know that the bases of the parallelogram are parallel to each other. Parallelogram. So we can go ahead and indicate the parallelness of our diagram. So now we can refer to all of our flat lines as our parallel lines. So all of these. So when we talk about the angles in this image, we can say above the parallel, below the parallel. But then what are the other, if you have a set of parallel lines and you draw a line across it, like through them, what do we call that? A transversal, right? So I'm gonna, now I don't have all of the colors. I'm gonna use my lighter colors that I have on these. So we could call these transversals to the yellow line. But what else does it look like? Well, and we know this because the problem told us parallelogram. There's actually parallel lines to the pink line, right? So if this is a parallelogram, this would be parallel to that. And therefore, all of those lines going that direction will be parallel to each other, right? All right, parallelogram. At this point, do we think we could code more of our green angles? Do it. Yeah, do it. And hopefully this sound is oddly satisfying because it sounds like a game we play online when you choose a place to build. It like makes like a little scribble sound. All right, so green angles. Did I get all the ones that you got? Yeah? That's all of the angles that we consider congruent or equal to our green angle? Ooh, no. But you said I got all the ones you got. Or were you waiting for more instructions?
I spotted more.
What do you mean you spotted more?
Since they're like 6 parallel, there must the opposite angles must be congruent.
Oh, in a parallelogram. Now, is this a rule? Is this like always true?
If both opposite sides.
So, do we still have put you on the spot. But do we have that shapes, that polygon graphic organizer? So here, if we don't already have that opposite angles are congruent or equal, we should indicate that on our polygon resource page, right? So if you don't have that, if that isn't... Now, there's another way we can justify why this angle would be equal to the green angle, not using the parallelogram rule. What? Sorry, say again. Yeah, that's using the parallel line rules, and I agree, but let's imagine we didn't know the parallel line rules. What if you were helping one of my 7th or 8th graders? Like 7th or 8th grade math. What is a rule that they should know before they've ever learned about parallel line relationships? Anytime you say alternate, you're talking about parallel line relationships. Because same side or alternate, like that's all parallel line relationships. Guys, you're probably going to have a face palm when, like, if I have to give this to you. This angle and this angle, right? They're vertical, right? So on top of our parallelogram rule, on top of our parallel line with a transversal rule, we have vertical angles. So indicate these.
Pardon the interruption. Lee Harris, please come to the office.
Here.
Lee Harris, please come to the office.
It's the bottom left angle, so I think out here. Am I missing any? Now do we have all of them? Yes? Well, let's change colors, and then we'll see like if we have anything left over. So let's go, you want to go blue? We all got blue on our thing? Let's go blue. I'll have to give blue back to this set. I forgot to ask the office. Let's go top left, but this little, like the top part. Right, this one. Let's go blue right there and have you try to shade in all the blue angles. Top left. Oh, I didn't think about blue and yellow making green. I'm silly. Did I get them all? Why no? Yeah, I missed the verticals again. Because they weren't top left. Instead of being top left, they were bottom right. But this again supports... What rule do we know about vertical angles cut by a transversal? Alternate interior angles are congruent, right? This is supporting that rule. It is driving it home that we can prove, a thing we're going to do this year is mathematical proof. We can prove, not by using the rule that we're trying to prove. So guys, this activity is pushing us towards understanding how to write a proof. But if I asked you, why are these blue angles congruent? And you say parallel lines cut by a transversal have alternate interior angles that are equal. And I say, prove it. You can't say, because they're parallel lines cut by a transversal with alternate interior angles. You can't prove something by saying the same thing again. So as we start to develop our skills of mathematical proof, and I think you guys did some in Math 1, right? So I don't really like flowchart proofs, to put it out there right now. 2-column tends to be better, like for our brains to understand. If you prefer flowchart, you're welcome to use flowchart. But even when the homework and things say flowchart proof, I normally say 2-column it if you want to. But to prove something, you have to prove it in a different way than the result that you're trying to say, this is true. So if we set this up and used our vertical angle relationships, that would be a way to prove it. And if you are going to claim opposite angles of a parallelogram are congruent to each other, and somebody says prove it, right, you have to use a different method. Finish out your shape just to make it look nice and pretty. I don't know, I think I'm going to use purple. So we said all the different ways this could be justified was alternate interior angles, which is from parallel lines cut by a transversal. We said vertical angles. There's actually another, now that we've got all of these different colors indicated up here, there's like another relationship that we should kind of see. That you might already know about parallelograms, but this is kind of pushing us to make sure that we know it. You said 2 words. So this kind of drives us to a CPCTC situation, which is so much fun to say. Congruent parts of congruent triangles are congruent, which actually, it's corresponding parts. Just by the way, most people like to say congruent parts. But again, like with proof, you can't start your statement with congruent parts when the ending of your statement is are congruent. So be careful. CPCTC is corresponding parts, right? All right, so, well, crap, I forgot a couple angles. I am not an artist, obviously. But to use that, the rule that you just said, what do we need to know first? To use CPCTC, what do we need to know first? We need to know that the triangles are congruent. Crap, guys, I forgot a blue, too.
Please excuse this interruption. Could I have Lucy Shivington to the office? Lucy? Thank you.
All right, so this idea of congruence. What does it mean for 2 things to be congruent? Like, there is a difference between congruence and equality. And this still messes with me. Like, I'm not doing the teacher thing. I'm serious. It still kind of plays with my brain of like, well, those things are equal. Are they congruent? I'm not sure. Like, so still, I'm like trying to master this. You know, some of this is me being a teacher to help you guys get in that brain, that like mindset. But I still do have to like catch myself, right? Like I have to double check. Am I following the legit what congruent means? How is congruence different than similarity? Sorry, I got a text coming in from the team. I just gotta check this really quick. What's the difference between similar and congruent?
I think congruence means like has equal angles and length assignments. Similarity means equal angles but not equal assignments.
Okay, similarity still has equal angles, but could be a different size, we're saying. All right, so we already kind of formalized this, but I just want to make sure that we actually see what is happening. See. So if we cover up a part of this and look only at like a set of parallel lines cut by transversals, we can see three different examples really of alternate interior angles being the same angle measure, right? So if we looked at this as a triangle with an exterior line, so this is tough, but like take this image and turn it into this, right? So take away some of those lines. We see that angle A would be congruent to what angle? D. And angle C would be congruent to E. So actually, here's another theorem that we're heading towards, and I like to overteach because y'all are smart and you can handle it. If I take this line and go rotate it so that actually I'm looking at this entire this. What do we know about that angle compared to angle B? Yeah, the exterior angle of a triangle is supplementary to that angle. So here would be the supplement, right? Because this is a straight line. But be careful, that doesn't make it equal. Like, you gotta be real careful about, are we fully split up? Because we would need to draw a line here to then get those relationships of alternate interior, right? Just be careful with, is the angle the total exterior angle, or is it just one of the alternate angles that we can relate congruently? So you guys know the triangle angle sum theorem. How many angles are, or how many degrees are in the angles of a triangle? 180. So take a second to read this. I talk too much. I had to reread that twice because I looked at the picture and I read it and then I was like, wait, I think there's a disagreement. So it said, now that we've proven the triangle angle sum theorem, we can always determine the third angle of the triangle, but the picture they gave us is sidelines, right? So I want you guys to chat with each other. Is there a way we can determine something about AC? Even if we can't determine exactly what it is, what can we determine? You're not talking to me, you're talking to each other right now.
Look into your polygons graphic organizer.
Absolutely.
You see that there's look underneath this scaly triangle. There's this formula where it shows like angle sum to 180. You just see that, like it shows that A plus B is greater than C and then B plus C is greater than A. So if you just try to like plug it in, you can try to find it.
So wait, what do you mean? Because you said that kind of fast. Can't tell if Eric caught it all. You said in the graphic organizer there was what?
Like under the graphic organizer, there's a section called scaling triangle where it describes one triangle. We wrote down something about like how there's some kind of equation here.
Should have drilled one more hole.
Take it out.
Should have drilled one more hole. Lost my tape. I swear I just saw it. Blue tape. Aha. I normally don't tape these together, and then I'm like, man, I should have taped those together. It would have been easier. that side CA, how it looks right now, doesn't matter. Looks in mathematics can often be deceiving. The only thing that we can trust 100%, and it's funny that we say it 100%, is the numbers, right? So even though CA might look, oh, it's like, I had a student the other day on a Math 7 homework trying to measure a side that they were given, do a conversion to the length that they were actually looking at on their ruler, and use that to measure for their homework, right? They were trying to like force a measurement. It doesn't, the pictures are often stretched weirdly or like just are made intentionally to throw you off. The only thing here we can trust is the 8 and the 6. So let's imagine this is 8 and this is 6, right? Is this a triangle? No. Okay, even though it's not a triangle, can we figure out what this is? Like this is a point and this is a point. This. Can we figure out what this is? What is it? It's the difference, right? It's the longer leg minus the shorter leg. So first things first, I know that 8 minus 2 is the difference. So if I make these like A and B, and I make B the bigger side just to make life easier, B, oh, that's really thick. B minus A is less than or equal to the third length, yeah, the C, the third length I'm looking for, is less than or equal to, I go all the way around here, whatever. Yeah, the sum, because this, no wait, is this right? Is what I wrote right? I'm wrong? I love being told I'm wrong, because it means my students are paying attention. Is this right? C should be smaller than A. That's what I wrote. Fight for yourself. I'm wrong. Fight for it. Why am I wrong? Well, that's convenient. Is this a triangle? No. So this, where we stand, this being the difference, cannot be what C equals. I did this on purpose because these are the mistakes my students like to make. This is just less than, because this is not a triangle. But what that means is, since this is 2, like for this situation, let's write this down. 2.000000001 would be allowed as soon as I lift this at all. I can make a triangle, a very skinny triangle, but I can make a triangle. I could have nice triangles that actually look like a triangle, right? Or this that I've now realized is super convenient about using that tape. But then what we're saying is we're hypothesizing this. So we said this has to be bigger than 2. But then at the same time, we're also saying it has to be smaller than, well, in this case, A plus B, 14. So would 13.9 be acceptable? Yeah. Would 14.1? No. Breaks the triangle. Triangle inequality theorem. Questions? Now this relates to what we call the Hinge Theorem. So you might want to jot down Hinge Theorem, since this is new for us. Like, it's up to you, really. Oh crap, before we do that though, let's test out if you actually can utilize what we just said. Some of these cannot be triangles. Your job is to figure out which ones do or do not work. So essentially give it a check mark that it works, or give it an X that it doesn't. You are welcome to come up to the board and actually cross things out or check mark things or whatever, but you're talking with each other to do this. I didn't really teach it yet. So I started talking about, but then I remembered we wanted to do an example of this before I teach you the Hinge theorem.
Then I don't understand the one you just told me.
So I appreciate you advocating for yourself. The other way to say the triangle inequality theorem is that the length of any two sides. We'll use this example because it actually works better. So what do you notice about if I go to make this into a triangle, and imagine that imagine the board stop right up top, right? I couldn't put a screw right at the top because I wanted to screw better than tape. So what do you notice about this triangle immediately? Yeah, it's isosceles, right? So if I say the third side is the distance between here, well, the difference, my lower boundary point is the difference between them. Well, if they're equal to each other, what's the difference? 0. So my shortest possible side would be like 0.0000, like 1, right? Very, very small number. I could almost reach 0. My biggest side, right, if I make it equilateral, great, nice, they're all equal, they work. But if I go all the way to the biggest triangle possible and break the triangle and just come back a scotch from it, like what would break the triangle is the sum of the two of them. So let's say these are both 10, right? Nice round numbers. Could the third side be 10? Absolutely, then it'd be equilateral. Could the third side be 19? Yeah, it'd be a pretty flat triangle. Could the third side be 20? No. It breaks it. But the other way to talk about this rule is, let's say the third side is 1. 10 plus 10, bigger than 1, because the shortest distance between 2 points is a straight line. So if I go from A to B in a straight line, that will be shorter than going from A to C to B, right? Always. So how this translates into a mathematical rule is 6 plus 8 will be bigger than the question mark. It's like just a rule of physics, right? The shortest distance between 2 points is the straight line. The addition of the two sides is not the straight line. But then 6 plus question mark has to be bigger than 8, and 8 plus question mark needs to be bigger than 6. If all of these check out, if the value that we chose for the question mark checks out, we can use that value. If this is not true for every situation, it's not a triangle. It does not hold up. So what we can do is test these down here.
Wait, so this is the one you're talking about?
Depends. I mean, there are multiple rules. That is a rule that we can use for any triangle. It doesn't just have to be scaling. Any triangle has to actually have that rule be true. So let's check. Is 5 plus 3 greater than the third side of your triangle? No. Immediately, this breaks. Imagine this. We've got 5 and 3, and the distance between these endpoints is 10? Right? Like it broke, right? Like literally broke. The furthest you could go is the sum, and even then that's not a triangle. So even if they said 5, 3, and 8, that wouldn't work, right? If it's equal, that would not work. So 1, we can throw out right away. Throw this out, get out of here. Try the others on your own. Check them. Can they work to be triangles? So I will tell you, my smartboard's being a little glitchy. Every now and then, like, it won't write. See how it like gapped? So just don't worry about it. I don't know what's really going on. Just like keep going when it glitches like that. Oh yeah, that's like the example that we just talked about in 1. Sweet. See? Yeah, it just glitched out, right? You drew a check mark. Still true, though, right? Still true. So, time to play with something. When we make a triangle, and if I don't drop it, we can kind of observe a lot of different things about how it behaves and how like. So as I'm moving this and the angles are changing, if I move it in, this angle is getting bigger or smaller. This spot, this angle where my finger is, from here to here, what has happened to the angle? Oh yeah. Grab C. Let's grab some graph paper. If you don't have it, you should have it. But if you don't, grab it. Go ahead, and if you don't have a ruler, I can grab you one real quick. Let's. Man, I don't think I'm gonna get to really teach the Hinge Theorem today, which is fine. Like we can come back to it tomorrow. But this is like what we're trying to get to. Draw a line across your paper. So like, you know. Sorry, some of my rulers have been chipped because kids have sword fought with them. And then let's draw another side of our triangle. And if I make a third side down to here versus a third side out to here. Now we can get protractors if we need. Now your triangle might look slightly different, right? Because we're just sketching this quick because I only have 4 minutes left and I'm acutely aware that I'm running out of time. Acutely aware, because we're talking about angles. So if I look at this triangle and say, well, this side obviously stays the same because I could use it for the small triangle or the big triangle. But if I look at my, you guys don't necessarily have to highlight this. I'm just trying to make us look at the right stuff. If I look at my original green side versus the extended green side, right? What happened to my green edge? it increased. If I compare it to the angle across the shape, which is everything we're going to do when we get to the point of trigonometry. Now, first we would have to make this into a right triangle, but we'll get there. That's not actually that difficult. What happened to the green angle when the green side got bigger? What? This green, the peak angle, if we call this angle A, between my first triangle I drew and my the whole big triangle. What happened to BC, did you guys say? What happened to BC? Did it get bigger or smaller? Bigger, right? Prime is always the new point. So guys, here's new, might be new notation for you, might be review. Prime is always newer, right? Original, prime. So BC got bigger. What happened between A to now A prime? Got bigger. Imagine that this is a door and a doorway, right? The door should be the same width as your doorway, so it shuts. If the doorway, the door, and the distance between them form a triangle, when I open the door, does the door or door frame change size? Well, I guess I probably emphasize that weird. No, right? Like the door and door frame don't change sizes. Like if I open that door right now, does the door change sizes? No. If I open the door, does the frame change size? No. But what does change? The length between, because if I open the door 10 degrees, do you guys leave? No, so 10 degrees, you can't leave class. What if I open the door 20 degrees? 30 degrees? 40 degrees? Probably maybe because y'all are skinny. So, guys, the Hinge Theorem, guys, these are hinges, right? It's not a mathematician's name. It's the name of the hardware. The Hinge Theorem tells us if we have a triangle and the lengths of the legs that are adjacent to the angle do not change, right? If these lengths do not change and the angle grows, what happens to the opposite side? It grows. That's the Hinge Theorem. In its most basic format, the Hinge Theorem is trying to get us to realize that the longest side will always correspond to the largest angle. And just in the nick of time, I'm out of time. That is all the math we have time for today. So we'll pick up probably right here tomorrow. So the 1, 3, 4 homework, right? So the stuff from 1, 3, 4, and then tomorrow we'll do closure in class. So if we don't get it done, that'll be outside of class homework, but we'll probably get it done. We will be utilizing the Hinge Theorem tomorrow, but you do not have to have this idea mastered. All you really need to get in your brain right now is, okay, if we open the door further, the angle gets bigger. If we close the door smaller, the angle gets smaller, right? So the Hinge Theorem is saying, if I made my 9 into an 8, right, this angle would get smaller, and consequently, these angles would probably get bigger. At least one of them, if not both of them. I mean, it's kind of common sense, and I don't like saying that, but if I can't fit through the door at 10 degrees, open it to 30 degrees, right? That idea is kind of natural, but utilization of it is not necessarily natural. So we'll start practicing this, but yeah, we'll start here tomorrow. We'll do a couple more problems and then we'll jump into the closure.
Where are we doing our homework?
End of the week, I normally do with your guys' class because I can trust that you're probably doing your homework, or if you get way behind, you're a bit older than the 7th graders and just like you got to hold yourself accountable to catch up. Normally, like you guys can handle it better. So like it's okay if you get busy and get behind. You just got to get caught up. So this week has just been 1, 2, 3, and now 1, 3, 4. And I'll just collect those on Friday with the test. So. All right, guys. Thank you very much. Have a wonderful day.
Wait, can we check our answers? Like, we shall
Oh! That's really funny that you asked that. I had it ready. Literally. Here's your answers from last. Like, I had it ready. So, yes, tomorrow we will check answers. I will write it on a Post-it right now so I don't forget. Now, also, if you really want to know, I'm recording. So, as soon as this video gets uploaded to YouTube, you could just go to the very end of the video and check your answers there.